We thought we knew the universe's scale. In 2004, Hubble's ultra-deep field stunned us with 10,000 galaxies and shaped estimates of 2 trillion across the cosmos. But everything about that benchmark was limited, just a pinpoint in visible light, missing what lay hidden in dust and redshift. Now, the James Webb Space Telescope has shattered those boundaries. In a single 250-hour campaign, Webb's Cosmos Webb mosaic revealed not 10,000, but nearly 780,000 galaxies across a patch no bigger than 3 full moons, stretching back 13.5 billion years. The scale isn't just larger, the rules themselves have changed. How could so much structure and maturity appear in what once looked empty? This is how the JWST just redefined how big the universe really is. In 2004, astronomers pointed Hubble's gaze toward a seemingly empty patch of sky in Fornax and let it stare for over 11 days. The result, known as the Hubble Ultra Deep Field, became an icon of modern astronomy. What looked like a blank void was revealed to hold nearly 10,000 galaxies, each a sprawling island of stars, some shining from over 13 billion years ago. This single image, just a speck against the night, became the foundation for estimating that the observable universe contained as many as 2 trillion galaxies. For years, the ultra-deep field was the best map we had of the distant cosmos, a window into the universe's childhood. Every point of light was not a star, but a galaxy, each with billions of its own suns. Yet Hubble's vision, as deep as it reached, was fundamentally limited. Its 2.4-meter mirror captured mostly visible and ultraviolet light. The most ancient galaxies, their light stretched by the expansion of space, had faded into the infrared, beyond Hubble's reach. And between us and those distant beacons lay clouds of cosmic dust, veiling entire populations of galaxies from view. Hubble's ultra-deep field, for all its detail, was just a sliver, shaped by the limits of its technology and the narrow slice of the spectrum it could see. The universe, it turned out, was hiding far more than we realized, waiting for a new kind of telescope to reveal what lay beneath the dust and beyond the visible. James Webb is not just a bigger telescope. It's a fundamentally different kind of observatory. Its primary mirror stretches 6.5 meters across, dwarfing Hubble's 2.4-meter dish and collecting more than 6 times the light. But the real breakthrough is in its eyes. Webb is tuned to infrared, a spectrum that lets it pierce through cosmic dust and catch the faint, stretched light of the earliest galaxies. Light invisible to Hubble. Where Hubble's vision was like peering through a keyhole, Webb's is more like stepping back to take in a massive mural. To put the leap in perspective, imagine the Hubble ultra-deep field as a photo on a single sheet of paper. At the same depth, Cosmos Webb would fill a mural 13 feet tall and 13 feet wide. The Cosmos Webb program harnessed Webb's power for an unprecedented survey. Over 250 hours of observing time, meticulously scanning a patch of sky about 3 times the area of the full moon. Thousands of exposures were stitched together into one seamless mosaic, creating the largest and deepest panoramic map of the universe ever assembled. Within this single field, astronomers cataloged nearly 780,000 galaxies, each a city of stars, some shining from less than 400 million years after the Big Bang. This isn't just a bigger picture, it's a new kind of atlas. The map is deep enough to reveal the universe's faintest, oldest structures, and wide enough to capture the grand architecture of cosmic filaments, clusters, and vast voids. For the first time, astronomers can study not just isolated galaxies, but the full sweep of cosmic structure across billions of years, all within a single, continuous frame. Webb's infrared vision and expansive reach have delivered a new window into the universe, one that transforms our understanding of both its vastness and its hidden depths. Within the vast cosmos Webb mosaic, the nearby universe comes into focus as a realm of mature galaxies, tangled mergers, and colossal superstructures. Here, astronomers have found galaxies in their prime, grand spirals, smooth ellipticals, and irregular shapes caught mid-collision. The scale of this map allows researchers to trace how these galaxies gather into titanic filaments and clusters, forming the backbone of the cosmic web. Yet among these familiar shapes, one discovery stands apart: a system known as the Infinity Galaxy. This extraordinary object, catalogued at redshift 1.14, reveals a figure-8 silhouette. Two disk galaxies colliding almost head-on. Each galaxy remains visible as a compact red core, circled by rings of stars and gas, their orbits twisted by the force of their encounter. The collision, estimated to have taken place about 50 million years ago, is not just a spectacle of cosmic violence. It has created conditions never captured so clearly before. Between the two galactic centers lies a vast cloud of ionized hydrogen, glowing with the energy of a hidden engine. Deep JWST and Chandra observations have pinpointed the signature of a supermassive black hole not in either nucleus, but lodged in the space between. Embedded in the gas, its velocity matching the surrounding material to within 50 kilometers per second. This off-center black hole, weighing in at about 1 million times the mass of the Sun, is joined by two more. Each original galaxy harbors its own active supermassive black hole, confirmed by their broad hydrogen emission lines. The configuration is striking. 3 hungry black holes, all active, yet only one sits outside a galactic core, nestled in the aftermath of the collision. The evidence points to a direct collapse origin. The black hole formed in place from the dense, shocked gas funneled by the merger, rather than being ejected or captured. Its presence, caught in the act by JWST's infrared eyes, offers a rare glimpse of how supermassive black holes might seed themselves in the chaos of galaxy assembly. The Infinity Galaxy stands as a testament to the power of a panoramic map. Only by surveying such a wide and deep field could astronomers spot such a fleeting, complex event. Its figure-8 form, with a black hole growing in the void between, hints that the universe's most massive engines may sometimes ignite not in the hearts of galaxies, but in the turbulent spaces where worlds collide. Now we journey deeper into the cosmos Webb mosaic, traveling back to a period astronomers call cosmic noon, an era about 10 billion years ago, when the universe was at its most prolific in forging new stars. The galaxies found here are not just energetic, they are organized, displaying a maturity that defies expectations. Webb's infrared vision is now revealing a startling contradiction. Galaxies that have already stopped forming stars, so-called quenched systems, appear in abundance at a time when they should be ablaze with stellar birth. These dormant giants, some with masses rivaling today's largest ellipticals, sit quietly amid a cosmic landscape that theory predicted would be dominated by youthful, chaotic systems. But the surprises do not end there. Webb has uncovered spiral galaxies with well-defined arms, their disks stable and symmetrical, even at redshifts between 2 and 3. In cosmic terms, this is just a few billion years after the Big Bang. Conventional models suggested that it would take far longer for the universe to build such ordered structures. Yet here, spiral arms wind gracefully around dense cores, and some galaxies already display central bars, signs of a settled, mature disk. The data show that disks capable of supporting these features were common much earlier than anyone anticipated. This early order is not just a matter of visual elegance. The presence of stable disks and quenched giants at cosmic noon means the processes that shut down star formation and shaped galactic structure must have operated with remarkable speed. The timeline for building complexity in the universe is shrinking. Each galaxy in this era becomes a clue, an evidence piece forcing astronomers to reconsider how quickly and how often the cosmos can leap from chaos to order. The map is not just richer, it is rewriting the rules of how galaxies grow up. At the edge of what Webb can see, the record for the farthest confirmed galaxy now belongs to Jade's GS Z14-0. Its light began its journey just 290 million years after the Big Bang. Not far behind, MOEM Z14 sets a new benchmark at 280 million years. Both galaxies have been spectroscopically confirmed, their distances locked in by sharp Lyman breaks in Webb's NIRSpec data. But the surprises go deeper. ALMA has detected oxygen emission in Jade's GS Z14-0, revealing that heavy elements were already present at this early moment, evidence that at least one generation of stars had already lived and died. These galaxies shine with the brightness of hundreds of millions of suns, compacted into tiny, intense starbursts. Their existence and their chemical fingerprints suggest that galaxy assembly and stellar evolution began at a speed that defies the standard cosmic timeline. In the first 300 million years, the universe was already busy forging complexity. The discoveries flooding in from Webb's new map are forcing astronomers to rethink the story of how the universe built itself. Galaxies and black holes are now known to have formed earlier and grown faster than models allowed. Even the most distant confirmed galaxies, like Jade's GS Z14-0 and MOEM Z14, are already shining with heavy elements just 280 to 290 million years after the Big Bang. This means that the cycles of star birth, death, and enrichment had to start almost immediately, compressing what was thought to be a slow, billion-year process into a cosmic sprint. The standard cosmic timeline, once a slow march from simplicity to complexity, now looks more like a rapid-fire sequence of assembly and transformation. The pace of reionization, the growth of massive halos, and the seeding of black holes all demand new explanations. The universe's first chapters are being rewritten, and the questions that remain will drive research for years to come. In just 250 hours, the James Webb Space Telescope's Cosmos Webb survey mapped nearly 780,000 galaxies, almost 80 times more than Hubble's ultra-deep field revealed in 2004. This infrared panorama exposes structures and galaxies stretching back 13.5 billion years, including record breakers like Jade's GS Z14-0 and MOEM Z14, both seen less than 300 million years after the Big Bang. JWST data show that mature spirals, massive mergers, and heavy elements appeared far earlier than existing models predicted. Yet, key questions remain. How did galaxies and black holes grow so quickly? What role did dark matter and feedback processes play? The timeline for cosmic evolution is being rewritten with every new observation. Still, this map covers just a small patch of sky, reminding us that our universe is even larger and more complex than we once imagined, and much remains